be a measure space. 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 And be greater than be a real number. P is greater than P is greater than 0. Means P is greater than means a positive. B be a be a be a real number. Be a real number. Be a real number. Be a real number. A real valued function f is defined. A real valued function. Real valued function. Be a real valued function. F defined on x. F is defined on x. F is defined on x. Defined is said to be class. Is said to be class LP x mu is said to be LP x comma mu if integration on x mod f whole power p d mu less than infinity. Said less than infinity. Less than infinity. Less than infinity. Thus the class LP x comma mu equal to within the set equal to f such that integration from x mod f whole power p d mu is less than infinity. The class of LP means f such that the integration x mod f whole power p d mu less than infinity. As the okay. This is denoted by already with the L of p class x mu or LP mu LP of mu or simply LP spaces. LP spaces. LP spaces means the class of LP. F such that what is LP spaces? F such that this is the definition. Integration x mod of p d mu less than infinity. Right. So L1M is the class of all functions integrable with respect to mu on x. So L1 mu is the class of all functions. What is that? This meaning is class of all functions, all functions, class of all functions, class of all functions is the class of all functions, all functions. Integrable with respect to integrable, no, integrable with respect to mu on capital X, on X, on X. Okay, next. The class of all measurable functions, the class of, the class of the class of all measurable functions, all measurable, or the class of all measurable, measurable functions, measurable functions, the class of all measurable, which are bounded almost everywhere on X, which are BDD. BDD means bound, which are bounded almost everywhere on X, everywhere on X, everywhere on X, everywhere on X is denoted by, is denoted by, is denoted by L infinity X, comma, mu. 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 X, comma, mu. R L infinity mu or simply or briefly L infinity, L infinity simply, right? Using these definitions, we'll prove one theorem. One theorem, that is theorem 1. Theorem 1. For p is greater than 0, for p is greater than 0, p is greater than 0. The collection LP, the collection LP mu is linear space. P, mu is linear space. Linear space. Linear space. Proof. 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 It is enough to prove the following. It is enough to prove the following. Enough to prove the following. The following. You have to prove the following. First one, F belongs to LP mu. F belongs to LP mu. LP mu. And A belongs to R. A belongs to R. A belongs to R. That implies AF belongs to AF belongs to LP mu. And second one is F belongs to LP mu. F belongs to LP mu. F belongs to LP mu. And G belongs to LP mu. G belongs to LP mu. LP mu. That implies their sum. Their sum means F plus G. F plus G. Both belongs to LP mu. Both belongs to LP mu. Consider the P equal to infinity. Consider the consider the P equal to infinity. P equal to infinity. And P lies between lies between 0 to infinity. Separately. Separately. Okay. First, so P equal to infinity. P equal to infinity. First case. Case 1 is trivial since F is measurable function. Is trivial. Is trivial since F is measurable functions. Since F is measurable functions. Measurable functions. Measurable functions. Since F is measurable functions. Which is bounded almost everywhere on X. Which is bounded. Means here BDD means bounded. Which is bounded. AE means almost everywhere on X. Almost everywhere on X. Almost everywhere on X. Then, so it is AF. Then, so it is AF, AF, AF for any A belongs to R. For any A belongs to R. A belongs to R. To prove second in this case, to prove second one, in this case, in this case, and in this case, in this case, let f comma g belongs to L infinity. Let f comma g belongs to L infinity. L infinity mu. If A equal to if A equal to if A equal to x belongs to x, small x belongs to capital X, such that f is not bounded. F is not bounded. BDD means bounded. F is not bounded. Is not bounded. Is not bounded. B equal to x belongs to is not bounded. B equal to x belongs to capital X, such that G is not bounded. G is not bounded. G is not bounded. G is not bounded. G is not. Then mu of A equal to mu of B equal to 0. Then mu of A equal to mu of B equal to 0. Also F plus G is bounded except on A union B. Then F plus G is bounded except on A union B. Except on A union B. Except on A union B. Since mu of A union B, since mu of A union B, mu of A union B equal to mu of A plus mu of B, that equal to 0, because mu of A is 0, mu of B is also 0, above 1. So we get F plus G is bounded. We get F plus G is bounded. F plus G is bounded almost everywhere on X. AE means almost everywhere on X. Showing F plus G belongs to this, showing F plus G belongs to L infinity mu. Infinity mu. L infinity mu is a linear space. Thus L infinity mu. L infinity mu is a linear space. LS means linear space. LS means linear space. Linear space. Linear space. Linear space. So now suppose let P lies between 0 to infinity. Separately we said no, that one. That condition we are using here. Infinity. Let F belongs to LP mu. Let F belongs to LP mu. F belongs to LP mu. And A belongs to R. And A belongs to R. A belongs to R. Means set of real numbers. That means A belongs to R. A belongs to R. Then AF belongs to LP mu. Then AF belongs to LP mu. This is page number 62. Page number 62. Page number 62. 62. Since integration x integration x AF whole power p d mu equal to integration x a power p d mu d mu integration x mod a whole power p mod f whole power p mod f whole power p d mu d mu d mu that equal to mod a whole power p mod a whole power p mod a whole power p integration on x mod f whole power p power p f whole power p whole power p d mu less than infinity d mu less than infinity. This is by definition or by definition. By definition. Right. Next. Infinity. Proving on. This is proving first condition. So To prove that, prove second, suppose second condition. We need to prove that second condition. To prove prove second condition. Let f comma g belongs to LP mu. Let f comma g belongs to f comma g belongs to LP mu. LP of mu. LP of mu. P of this. Write E equal to. All right. Write E equal to. Write E. Write E equal to. X such that x belongs to x belongs to equal to x belongs to capital X such that f of x is greater than or equal to mod f of x mod f of x is greater than or equal to mod g of x mod g of x mod g of x. So f equal to x minus e. F equal to x minus e. Then f plus g f plus g of x f plus g of x is less than or equal to 2 into mod f of x. 2 into mod f of x. 2 into mod f of x. For x belongs to B. For x belongs to x belongs to B. X belongs to B. X belongs to B. And f plus g and mod f plus g of x f plus g of x is less than or equal to 2 into mod g of x. Mod g of x. For x belongs to, for all x belongs to capital M. X belongs to capital M. Capital M. Thus, what is x here? F is x minus e is the f. X minus e is the f. Therefore, integration on x mod f plus g whole power p d mu that equal to integration e integration e means on integration e f plus g whole power p d d mu d mu plus integration f, that is e, this is f mod f plus g whole power p d mu is less than or equal to 2 power p integration e mod f power p d mu d mu plus integration f before this 2 power p 2 power p 2 power p g power mod g whole power p d mu d mu d mu is less than or equal to is less than or equal to 2 power p. You need to take both the common. Need to take 2 to the power of p is common. Common. So integration x mod f power p d mu d mu means with respect to d mu integration x, yeah, x mod g power p mod g power p d mu d mu g power p d mu, which is less than infinity. Is less than infinity. So this gives this gives us this gives us proving second. This gives us f plus g. F plus g belongs to LP mu. Easy theorem, an important theorem. 10 marks. Next, definitions. Next, definitions. Definition. 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 Page number 63. Yes. Page number 63. Suppose L is a real linear space. Let L is a real linear space. Linear space is a real linear space. Real linear space. By norm on L. By norm on L. On L. We mean a mapping. We mean a mapping. Mapping Mapping is nothing but function. Mapping. Norm. Norm. L to R means linear space to set of real numbers. L to R. L to R. Such that. ST means such that. First one. First one. Norm x greater than or equal to 0. Norm x is greater than or equal to 0. Equal to 0. For all x belongs to capital X. X belongs to, for all x belongs to capital L. Second one. Norm x equal to 0. Norm x equal to 0. If and only if x is 0 vector in L. Norm x equal to, norm x equal to 0. If and only if and only if x is the 0 vector in L. X is the 0 vector in L. 0 vector in L. 0 vector in L. Third one. Norm alpha x equal to, norm alpha x equal to, norm alpha x equal to. This can be written as mod alpha into norm x. Norm x. If alpha belongs to set of real numbers, x belongs to R. If alpha belongs to set of real numbers, real numbers, and x belongs to L means linear space. Fourth one. Fourth one. Fourth one. Fourth one. Norm x plus y equal to, norm x plus y is less than or equal to norm x plus norm y. Norm x plus norm y. Norm x plus norm y. X plus norm y. So a linear space L is together with a norm defined on its key is called normal linear space. NLS means normal linear space. Next definition. Definition number 2. Definition 2. Definition number 2. Let f be a measurable function on measure space. F be a measurable function measurable function on measure space. Function on measure space. Measure space. Yes. Yeah. Triplet X, A, mu. A triplet X script A, mu, X, A, mu. By an essential upper bound, by essential upper bound of, upper bound of F, upper bound of F. We mean an extended real number V. We mean, we mean, we mean an extended real number V. An extended real number V. Real number, extended real number V, such that F is less than or equal to V. F is less than or equal to V. Almost everywhere on X. AE. AE means almost everywhere on X. X. The infimum of all the essential. The infimum the infimum the infimum of the infimum of the infimum of the infimum of all the essential upper bounds. The essential of upper bounds. Upper bounds. Upper bounds. For F is called the for F is called the essential supremum of F. Essential supremum of F. Essential supremum of F. And is denoted by S supremum of F. And it is denoted by this is denoted by S supremum of F. S supremum of F. Thus, essential supremum of F is defined is defined. Infimum of INF, infimum of V such that F is less than or equal to V. Almost everywhere on X. On X. On X. Next. Next definition. So for short answer question purpose, this is short answer question. This is important. Short answer question 1. Page number 63. Page number 63. Page number. Short answer type important. Prove that. Prove that. CAQ. Prove that. Prove that. F less than or equal to. F less than or equal to. Essential supremum. ESS. Essential supremum. Supremum of S. Prove that F is less than or equal to essential supremum of F. AE means almost everywhere. Right? Proof for short answer type question. Important. Proof. Proof. So if essential supremum of F equal to, if essential supremum of F equal to plus infinity, the result is trivial. The result is trivial. Result is trivial. If essential supremum of F is, if essential supremum of F equal to minus infinity, then F is less than or equal to V. Then F is less than or equal to V. Less than or equal to V. Almost everywhere. AE means almost everywhere. For all, small v belongs to set of real numbers. So that, so that, so that, so that F equal to minus infinity almost everywhere. Almost everywhere. And hence, and hence, and hence, F equal to essential supremum. Essential supremum of F. F. In this case, in this case, in this case, in this case, if essential supremum, if essential, ESS means essential, supremum F equal to S. What is right? W, right, right, right. En equal to E suffix n equal to X such that f of x greater than s plus 1 by n, 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 and e equal to, and e equal to, and e equal to x such that f of x, f of x, x such that f of x greater than s. What is s? S is the essential supremum of f, that meaning. Greater than. So that e equal to, so that e equal to, so that e equal to, so that e equal to. Union n equal to 1 to n. Union n equal to 1 to n. 1 to n. N equal to n. E n. E suffix n. E suffix n. N. But by the definition of yes, but, but by definition of, definition of, definition of yes, by definition of yes, by definition of yes, by definition of yes, mu of en equal to 0. Mu of en equal to 0. En equal to 0. For each n, for each n, sorry, for n, each n, and hence m of e equal to 0, and hence m of e equal to 0. Mu of e equal to 0. Mu of e equal to 0. Thus, thus, mu of thus, mu of x such that f of x is greater than 0. Of x is greater than 0. X is greater than 0. That equal to 0. Proving f of x is, this proving, this proving, this proving f of x is, this proving f of x less than or equal to s. What is s? S is the essential supremum of f. Almost everywhere. AE means almost everywhere. Uh, that is that is F is less than or equal to essential supremum of F. Essential supremum of F. Almost everywhere. This completes the proof of theorem. Hence proved. Hence proved. Right. Next. Next. Definition. Suppose. Definition. Definition. Suppose F belongs to LP mu. Let F belongs to LP mu. LP mu. F belongs to LP mu. F belongs to LP mu. It's LP norm. It's LP norm. LP norm. Denoted by denoted by denoted by norm F suffix P is defined by is defined by is defined by norm P norm P norm P equal to integration mod F of P d mu whole power 1 by P 1 by P. Second one second one second one. For F belongs to L infinity mu power. F belongs to L infinity mu. L infinity mu. It's L infinity norm. It's L infinity norm. Page number 63. 63. And L infinity norm. Norm. Denoted by norm infinity. Denoted by denoted by norm F infinity. Norm infinity. Okay. Denoted by norm is defined by 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 norm F infinity, F infinity equal to essential supremum of essential supremum. ESS means essential, SUP means supremum of essential supremum of mod F, mod F, where essential supremum of F is denoted by essential supremum of F. We prove the some inequalities needed to prove norm P and norm infinity is a fact satisfy the Holder's inequality. First one is Holder's inequality. Most important for 10 marks. Holder's inequality. Theorem number. Theorem. Theorem. Holder's inequality. Holder's. Holder's inequality. Holder's inequality. Suppose P and Q are non-negative extended real numbers. Let P and Q are non-negative, non-negative. P and Q are non-negative extended real numbers. Extended real numbers. Extended real numbers. Extended real numbers. Non-negative extended real numbers. Such that ST means such that 1 by P plus 1 by Q that equal to 1. In this case, P and Q are called conjugate indices. In this case, P and Q are called conjugate indices. If F belongs to LP mu, LP mu, and G belongs to and G belongs to and G belongs to G belongs to LQ mu, LQ mu, LQ mu. Then FG belongs to then FG belongs to L1 mu, L1 mu. Also, also norm FG, norm FG, norm FG less than or equal to norm F, norm F P into norm G, norm G Q. Right. Proof. Proof. Page number 64. Page number 64. Page number 64. Proof. Most important for 10 marks question. Right. First, prove the lemma. We need to prove the lemma first. We need to prove lemma. What is lemma? Lemma is a sub-theorem. To lemma. Lemma. If A is greater than or equal to 0, if A is greater than or equal to 0, B is greater than or equal to 0, greater than or equal to 0. Lambda lies between 0 and 1. Lambda lies between 0 and 1. 0 less than lambda less than means the value of lambda is lies between 0 and 1, meaning then a power lambda, a power lambda, b power 1 minus lambda means lambda less than or equal to lambda a plus 1 minus lambda b, 1 minus lambda b. 1 minus lambda. The proof of lemma. What is the statement? This is proof. Proof of lemma is let z of t equal to z of t equal to let z of t equal to 1 minus lambda, 1 minus lambda plus lambda t, lambda t minus t power lambda, t power lambda. The t is greater than or equal to 0, or t is greater than or equal to 0. Then z dash of t, z dash means differentiation. Z dash of t, then z dash of t, that equal to z dash of t equal to z dash of t equal to lambda into 1 minus t power lambda minus 1, lambda minus 1. Since lambda minus 1 is 0, lambda minus 1 less than 0. We have z dash of t, we have z dash of t, z dash of t, z dash of t less than 0, less than 0. For t less than 1, for t less than 1. Z dash of t is z dash of t is greater than 0 for t greater than 1. T is 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 greater than 1. Therefore, z of e is monotonically decreasing. Therefore, z dash of t is monotonically monotonically, monotonically, decreasing, decreasing function in closed interval 0, comma 1. Right. So, and monotonically increasing in monotonically monotonically increasing increasing in 1, comma infinity, comma infinity. Hence zt is greater than or equal to z1. Hence z of t is greater than or equal to z of 1. For all t is greater than 0. So that is 1 minus, that means 1 minus delta, 1 minus delta plus lambda t, plus lambda t minus t power lambda, t power lambda greater than or equal to 0. For all t is greater than 0, greater than or equal to, for all t is greater than or equal to 0, t is not equal to 1. Okay. With equality only t equal to 1. Equality. So if b equal to 0, inequality in the lemma. If b equal to 0, b equal to 0, if b equal to 0, the inequality in the lemma is obvious, is inequality in the lemma obvious, the obvious, by the obvious, obvious, obvious. If b is not equal to 0, b is not equal to 0, taking t equal to a by b, taking t equal to a by b, a by b, inequality above paragraph field, inequality, equality. So 1 minus lambda plus lambda into a by b, lambda into a by b, lambda into a by b, minus a by b whole power lambda, a by b whole power lambda is greater than or equal to 0. We are substituting this in this case, right? Which implies inequality of the lemma, and the equality holds if equality holds, equality holds a by b equal to 1, a by b equal to 1. Now prove the theorem, hence prove lemma. Now prove the theorem. to them. First of all, P let P equal to what? P equal to what? So Q equal to infinity. Q equal to infinity. So that the hypothesis gives F belongs to L dash mu. Hypothesis gives F belongs to L dash mu. Dash mu. G belongs to G belongs to L infinity mu. L infinity mu. L infinity mu. Therefore, G is essential bounded on X. Therefore, G is essential. ESS means essential. BDD bounded on X. Essential bounded on X. So G is a measurable function bounded almost everywhere on X, and therefore integrable with respect mu. Thus, that is G belongs to that is G belongs to that is G belongs to L dash mu L dash mu, and F comma G belongs to L dash mu. F comma G both belongs to L dash mu L dash mu L1 mu or L1 mu or L dash mu. The short of the question one. Huh? So mod Fg Fg is less than or equal to essential supremum essential supremum essential supremum bounded on X essential supremum on X essential supremum X. X. So that integration X mod Fg d mu mod Fg d mu less than or equal to essential supremum of G essential supremum of G essential supremum of G supremum of G into integration X mod F d mu proving 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 norm Fg proving proving norm Fg norm Fg L Fg L is less than or equal to less than or equal to less than or equal to norm G infinity norm F F1. Thus the theorem is proved in this case. Thus the theorem is proved in this case. Assume let P is lies between 1 to infinity 1 to infinity. Then Q is also lies between 1 to infinity. Q is also infinity. First, we shall suppose F belongs to yes, F belongs to LP mu. P mu. F belongs to LP mu. So from here onwards, we'll prove so on. Homework you do this one. Rest. Next, page number 65. Page number 65. Theorem 3. Theorem, theorem 3. Minkowski inequality. This is also important for 10 marks. Theorem 3. Homework. So, for 10 marks question. 10 marks. 10. Next, page number, page number, page number 3, page number 4, page number 67, page number 67, page number 67, theorem 4, 5, 6, theorem 5, 6, theorem 5, 4 mark for 10 marks. Theorem 6, 6. This is also homework for 10 marks. Okay. Need to take. This is as homework. Right. I'm leaving you. Okay, thank you. Thank you very much.